Okay, the three dimensionless parameters, the Knudsen number, Mach number and Reynolds number can be related as follows. What will, so here we would like to relate Knudsen number, Mach number and Reynolds number. They are related as follows. So Knudsen number is K, which is the specific heat ratio, pi divided by 2 square root into Mach number divided by Reynolds number. Okay. So this is how the three different dimensionless parameters are related. We can in fact mathematically show this. We can start from the left hand side. We can write Knudsen number equal to lambda divided by L. Lambda is the mean free path and L is the length scale of the flow. We can write lambda as half, we can write nu 2 nu over C bar into 1 over L, because we know that nu is half lambda into C bar. Okay. This is what we know. So we can write 2 u over C into u over nu over UL. Okay. This is C bar. So this is nothing but, this term is 1 over Reynolds number, right. So you can write 2 u over C bar into 1 over Reynolds number. Now we can write this as 1 over Reynolds number into u over Cs into 2 Cs over C bar. Okay. And we can also write this as u over Cs is the Mach number, right. So this is Mach number divided by the Reynolds number into 2, Cs is square root of K RT, K is the specific heat ratio, okay, K RT divided by 3 RT. So this can be approximate, this will be written as 2 K over, you can make it 4 K over 3 square root into Mach number over Reynolds number. This can be approximated as K pi by 2 into Mach number over Reynolds number. Okay. So this is how we could prove the relationship between three different non-dimensional parameter, right, the Knudsen number, Mach number and Reynolds number. So let us look at this plot that shows how these three numbers are related. It also gives you an overview of what happens to the flows at micro scale. In the x axis we have the density ratio n over n0, where n0 is the density at standard conditions, standard temperature and pressure. On the left hand y axis here you have the characteristic dimensions L in beta. On the right hand side you have the L over D ratio, L is the characteristic length scale and D is the molecule diameter. On the top you have delta over D, delta is the spacing between molecules and D is the diameter of the molecule. Now below, if you look at this dotted line here, okay, this dotted line, on the left hand side the gas is considered as dilute gas, okay, where the delta over d ratio is greater than 1, delta being the separation distance, d being the size of the molecule is greater than 1. So it is called dilute gas, and on the right hand side we have dense gas. Okay, here is the dense gas. If you look at this dotted line here, above this line the continuum theory is valid. Okay, yesterday in the earlier we looked at the continuum theory. We said that for liquid, if the characteristic length scale is greater than 10 nanometer, we can say that the flow is continuum, and if for the gas, if the characteristic size is greater than 1 micron, we can consider flow to be continuum. Where do we for the flow to be continuum, first we consider that what if we consider the point properties, we told that let us assume there are 10 to the power 4 molecules in a cubic space, cubic control volume. Okay, that is a sampling volume that we talk about, and for both liquid and gas we know the number density. So we can find out what should be the characteristic length scale of that point volume, okay, the cubic volume, so that the fluid will be continuum. And for the gas we found that the characteristic length scale is about 70 nanometer, and for liquid we found that it should be around 10 nanometer. Then we looked at the transport properties, and looking at the transport properties we saw that for liquid the characteristic distance should be around 1 micron, and for gas the characteristic length scale should be 1 micron, above which fluid can be considered continuum, and for liquid the characteristic length scale should be above 10 nanometer. Okay. So above this dotted line it satisfies that the flow can be treated as continuum above this line, and below this line we consider significant statistical fluctuations. Okay. Now if you look at these lines, these are called Nordsen number lines, these 3 lines. Okay. Now above this line we have the Navier-Stokes equations applicable, and the no slip at the boundary can be applied. So in which case we have Nordsen number less than 0.001. Between Nordsen number 0.001 and Nordsen number 0.1 we have Navier-Stokes equation applicable, but with a slip at the boundary. Okay. And between 0.1 and 10 we have transitional flow, where we cannot use the Navier-Stokes equation that we normally use, it needs to be modified, and if the Nordsen number is greater than 10 we get into free molecular flow. Okay. So that is what we learn from this plot. Now before we go ahead, I would like to correct something. Earlier we were talking about the force between 2 molecules, okay, and there was a small corrections that needs to be made here. So the force expression for the intermolecular force between 2 molecules 1 and 2 can be correctly written as this is 48 into epsilon divided by sigma into C12 into r over sigma to the power minus 13 minus D12 divided by 2 into r divided by sigma to the power minus 7. So this 2 was missing earlier when we were trying to write the expression for the force, the factor of 2 was missing, so that needs to be corrected. Now moving ahead, let us talk about the governing equations for the gas flows. We have talked about the kinetic theory of gases, where we can relate different parameters, different constants to understand how gases behave. Now let us look at the governing equations for the gas flows, okay, and we make some assumptions we assume that the gas is compressible, and we assume that the fluid to be Newtonian, and we say that the Fourier law of heat conduction is valid. So under those assumptions we write down the governing equations for gas flows. So we write down the governing equations for gas flows, okay, and we make some assumptions. So the assumptions are that the fluid is Newtonian, and it could be compressible, and the Fourier conducting gas, okay. So under those assumptions we can write the conservation of the mass, momentum and energy. Before we do that, as we discussed yesterday, we were talking about 5 different differential equations, 3 for momentum, 1 for mass, 1 for energy. So with 17 unknowns it is not possible to solve those equations unless we come up with the constitutive relationship, and these constitutive relationships they can only be postulated, they cannot be proved, okay. So what are those constitutive relationships? We relate the stress tensor to the velocity field, the heat flux to the temperature field, and we relate the energy with temperature, okay. So we write down the stress tensor tau J I, so that can be written as minus P into delta J I, so plus eta into delta U I over delta x j plus delta U j over delta x I plus lambda delta U k over delta x k into delta J I. So this is the stress tensor. We know what P is pressure. This is the called Kronecker delta function, and this will be 1 only when I equal to j, and will be 0 if I will be not equal to j, okay. Eta is viscosity, and we know all other parameters here. Similarly we can write down the heat flux Qi can be minus k into delta T over del xi, and the third constitutive relationship will be energy E will be Cv into T, specific heat at constant volume into the temperature and this is the internal energy, okay. And if you use these constitutive relationships into the mass, momentum and energy equations, we can write the conservation of mass as follows. So you can write it as del rho over del T plus del over del xi into rho ui to be 0, and we can write the momentum equation. In the momentum equation we will have rho, okay, where rho will be inside, so we will say del over del T into rho ui plus del over del xj into rho uj into ui, okay. So that will be equal to rho into Fi minus del P over del xi plus del over del xi into eta del ui over del xj plus del uj over del xi plus lambda into del uk over del xk into delta ji. Okay. So, this is the momentum equation. Similarly, the energy equation can be written. The energy equation, it looks like this: rho Cv, again the rho has to go inside. So, del over del T into rho T plus ui into del rho T over del xi will be equal to minus P into del ui over del xi plus phi is the viscous dissipation, plus del over del xi into k del T over del xi, where the viscous dissipation phi can be written as follows, where phi would be equal to half eta into del ui over del xj plus del uj over del xi square plus lambda into del uk over del sk square, and this is called the viscous dissipation. Okay. So, now we have we have 5 equations and 5 unknowns. What are those unknowns? Our unknowns are, so we have 3 uis and we have the pressure and temperature. Okay. So, these are 5 unknowns. So, we have 5 equations, so we can solve that. Okay. So, after that let us move on to talk about liquid flows. Okay. Liquid flows in micro scale is more complex as compared to the gas flows, because the molecular theory for liquid flows is not very well developed. Okay. So, there is no parameter equivalent to Nusselt number for gas flows in liquid flows. Okay. So, the liquid flows is not very well understood. Okay. And for example, if you consider viscosity of a fluid, when a fluid is passing through a microchannel, it has been observed that in some cases the viscosity in the microchannel, the apparent viscosity is same as the viscosity of the fluid, in, for example, in a macro scale flow situation. In some cases it has been found that the apparent viscosity in micro scale flows is greater than the actual viscosity. In some other cases it has been found that it may be less than the actual velocity. So, this is quite debatable. Okay. That is because the liquid flows in microchannels, the molecular theory is not very well understood. Okay. And the other important thing is that we know that if the length scale of the flow is larger than 10 nanometer, we can consider the flow to be continuum, but whether to, we can consider the fluid to be continuum, but whether to consider the flow to be continuum is not very clear. Okay. So, and if you consider another example, a fluid flowing through a relatively larger length scale can be considered as Newtonian. The same fluid, when it flows through a microchannel and the shear rate is too much above a critical value, then the Newtonian assumption break down. Okay. So, when it is shear too much, the Newtonian fluid assumption will break down. So, the critical there is a critical value of strain, okay, which can be written as the strain rate gamma c dot, which is equal to delta u over delta y. So, here we are talking about liquid flows. So, delta u over del y is 2 over tau, okay, when it is greater than equal to 2 over tau, and tau being the time scale of molecular interaction, then the assumption that a fluid is Newtonian, that breaks down. Okay. So, if let us say between two parallel plates, if you have a fluid flowing, okay, and we assume a quiet flow situation where one of the plate is stationary and the other plate is moving at a speed of 10 to the power 6 meter per second, then in that situation a Newtonian fluid will behave as a non-Newtonian fluid. Okay, so that the Newtonian assumption is going to break down. Okay, so that happens when the critical strain rate is twice the molecular interaction frequency. Okay, so if we consider two parallel plates, okay, and one is moving at velocity u and we say it is a quiet flow situation, then and when u is of the order of 10 to the power 6 meter per second, then the Newtonian assumption breaks down. Okay. But such speed is not possible at macro scale. To achieve a velocity of 10 to the power 6 meter per second is not possible at micro scale. So, the conclusion is that for most micro scale we can assume the fluid to be continuous. So, at micro scale such high velocity not possible. So, the conclusion is that micro scale flow is continuous. Okay. Now, having talked about the liquid flows, let us try to write down the governing equations for liquid flows. Okay. And in that case you can assume that the fluid is Newtonian. The density for the liquid does not vary that much, you can assume it to be incompressible, and we can also assume that the Fourier law of heat conduction is valid. So, under those assumptions let us write down the governing equations for liquids. So, governing equations for liquid flows. Okay. So, the first is the mass conservation equation. Our assumptions are Newtonian, fluid is Newtonian, it is incompressible and Fourier conducting. So, we write down the mass conservation equation, which will be del ui over del xi will be 0. The momentum equation will be rho into del ui over del t plus ui del ui over del xj will be equal to rho into Fi minus del P over del xi plus del over del xi into eta. Eta is the viscosity, del ui over del xj plus del uj over del xi. Okay. So, that is the momentum equation. Similarly, we can write the energy equation, which is rho Cv into del T over del T plus Ui into del T over del xi equal to del over del xi into k del T over del xi. Okay. So, this is the energy equation. Now, if you assume that the fluid remains at constant temperature, that means isothermal flow condition, then the energy equation can be decoupled from the momentum equation. So, if you want to solve a flow field where the isothermal flow condition is valid, then you can decouple the momentum equation from energy equation and you can just go ahead and solve the mass and momentum equation. Okay. So, this equation can be further simplified when isothermal flow condition is valid. So, isothermal flow further simplification possible, and the momentum and energy equation can be decoupled. Okay. So, that is about the governing equations for the liquid flow. Next let us look at another important concept in the fluid flow, which is the slip boundary condition. So, while solving equations, the mass momentum equations using for macro scale flow situation, we many times when you try to solve it analytically, we assume that no slip boundary condition is valid at the wall. So, that means at the wall the fluid takes the same velocity as that of the wall. Okay. Similarly, we have no temperature jump boundary condition, the temperature of the fluid at the wall is same as the wall itself. Okay. So, we have been using no slip, no temperature boundary conditions for analytical solutions, because analytically we get the same result that we get using experiments. So, they have been widely accepted, no slip boundary conditions have been widely accepted. Now, if you want to generalize the no slip boundary condition or slip boundary condition at the interface, okay, at the fluid solid interface, that can be done using Navier boundary condition. Okay. So, let us talk about Navier boundary condition. So, here we talk about Navier boundary condition in slip theory. Okay. So, the Navier boundary condition tells that delta u at the wall will be u velocity of the fluid at y tending to wall minus velocity of the wall. Okay. So, the velocity of the fluid right at the wall minus the velocity of the wall itself. So, that we can write as Ls. So, for now let us just write Ls and we will define it. So, delta u velocity of the fluid divided by delta y at the wall, and Ls is known as what is called slip length, okay, slip length. As you can see here in this figure here, we are considering a Couette flow situation, and normally we have no slip boundary conditions valid. So here we have the top plate moving at velocity u and the bottom plate is stationary. So the velocity of the fluid at the bottom wall is 0 and at the top wall it obtains the same velocity as the movement, the velocity of the upper plate. So this is what we have seen in fluid mechanics, this is known as no slip in Couette flow. Now if we allow partial slip to occur, okay, what will happen is at the bottom plate, instead of seeing 0 velocity we will see a finite velocity ub, okay, which is greater than 0, okay. And if we extend this profile into this bottom plate, okay, at some point this velocity would vanish and the distance between the top surface of the bottom plate and the point at which the velocity vanishes is known as the slip length for the bottom plate. Similarly at the top plate, if you allow slip we will get a velocity which is ut, which is smaller than u, okay. And if we extend the same profile into the top wall at some length, this velocity is going to be equal to the plate velocity, and the length at which this would occur is known as the slip length for the top wall, okay. So the slip length would depend on the interaction between the fluid and the surface, slip length depends on a particular surface, okay. So with that let us move on and talk about the slip in gas flows. So let us talk about the slip boundary condition in gas flows, okay. We know that the no slip boundary condition is valid when the Knudsen number is less than 0.001, and we can think of using Navier-Stokes equation where we may need to apply slip when Knudsen number is less than 0.1. So between 0.001 and 0.1 we need a theory to know what the value of slip is at the wall, okay. So very well, for gas flows we know if Knudsen number is less than 0.001 then no slip valid. So between 1 greater than between 0.001 less than Knudsen number less than 0.1 we need a slip theory, okay. And for gases we can write u gas minus u wall to be lambda into 2 minus delta b or sigma b divided by sigma b into del u over del y at the wall plus 3 by 4 into eta over rho T gas into delta T over delta x at the wall, okay. And we can write for temperature T gas minus T wall will be equal to 2 minus sigma T over sigma T into 2 K by K plus 1, K is the specific heat ratio into lambda divided by Prandtl number into delta T over del y at the wall. So, here most of the constant we recognize, eta is the viscosity of the gas and rho is the density of the gas here, and lambda is you know the mean free path. Here the new constants are sigma b and sigma t, which are known as the tangential momentum and temperature accommodation coefficients. And they can be defined as follows. We can define the momentum accommodation, tangential momentum accommodation coefficient sigma b as tau I minus tau r divided by tau I minus tau w. Similarly, sigma t, the temperature accommodation coefficient, dEi minus dEr divided by dEi minus dEw. So, the Ti term here is the tangential momentum of the incoming molecules, and Tv is the tangential, sorry, Tr is the tangential component of the reflected molecules. Tau w is the tangential momentum of re-emitted molecules which are adsorbed to the surface, and this term goes to 0 for a stationary wall. Stationary wall, this term goes to 0. Similarly, in sigma t, the dI is the energy flux of the incoming molecules, dEr is the energy flux of the reflected molecules, and dEw is the energy flux of the re-emitted molecules, okay, that have been adsorbed to the surface. So, so this is how we define the tangential momentum and temperature accommodation coefficients. If you look at this equation here, the second part of this equation, what we see is that if the flow is in stationary conditions, the velocity is 0, okay. So, the first term is 0, then if we apply a temperature gradient along x direction, then we would induce a slip along x direction, okay, and that is known as creeping flow. So, if you look at we call this is second term and this is the first term, and say that for stationary fluids the term 1 is 0 and term 2 in that case gives what is called as creeping flow, and it is possible to develop pumping action using creeping flow, which would be known as Knudsen pump, okay. For example, if you consider two channels here, single channel here, and here the temperature is T cold, here temperature is TH, here pressure is PC, here pressure is pH, and TH is greater than TC. So, you maintain a gradient in the x direction, let us call this x direction. So, dt del T over del x is positive, and if you look at this equation here, so that would induce a flow, so velocity of the gas with respect to the wall in the x direction. So, you would have a flow occurring in this direction u of the gas, and if you have let us say two reservoirs and you maintain a temperature gradient in this direction. So, you can induce a pumping action, okay, and that pump would be known as Knudsen pump. Okay. Now, if you talk about the tangential, the momentum accommodation coefficient, it takes care of the tangential momentum of incoming and reflected molecules, tangential momentum of incoming and the re-emitted molecules. Okay. If the sigma v goes to 0, okay, if sigma v goes to 0, what that means is that the tangential momentum of the incoming molecules is going to be equal to the tangential momentum of the reflected molecules. Okay. So, in other words, what that means is that the molecules do not impart any momentum to the wall. Okay. So, the conclusion is that in that case the flow can be considered as inviscid flow. So, there is no effect that is realized by the fluid in presence of the wall. Okay. Whereas, if we, and this situation can also be called as specular reflection, So, here if the molecules are coming at some tau I, they will be going at tau r. So, tau I is equal to tau r, right. So, this is the case of the specular reflection, and this occurs when the surface is very smooth, okay. Now, if you look at the other extreme where the sigma v is going to be 1, then the tangential momentum of the reflected molecules will be 0, and what that will mean is that the incoming molecules impart all their momentum to the surface. Okay. So, in that case you can say that this is a case of diffuse reflection. Okay. It is the case of diffuse reflection, and where gas imparts all its momentum. And if we say that perfect energy exchange taking place between the incoming molecules and the wall, okay, in that case the temperature accommodation coefficient sigma t will become 1. Okay. So, for perfect energy exchange, sigma t will be 1. Now, let us look at some of the surfaces where we can know what are the values of the momentum and the temperature accommodation coefficients. So, these are different gases which are interacting with different surfaces, and if you look at the values, you can see that the values of the both momentum and the temperature accommodation coefficients are in the range of 0.8 to 0.9 or little higher. Okay. So, that is the values of the momentum and temperature accommodation coefficients. So, with that, let us try to look at in the expression for the slip velocity, what are the importance of different parameters. Okay. So, in order to do that, we need to non-dimensionalize the slip equation. Okay. So, let us try to non-dimensionalize slip equation. So, we can choose a set of non-dimensional parameter. We can define x star as x over L, y star as y over L, we can define u star as u divided by some characteristic velocity u0, and we can define T star as T over T0. If you do that, then you can write the expression for the slip u gas minus u wall, and all are non dimensionalized now. So, this is going to be Knudsen number into 2 minus sigma v over sigma v into del u over del y. So, these are non dimensionalized, del u star over del y star plus, so this is at the wall, plus 3 by 2 pi into k minus 1 over k. So, this is specific heat ratio into Knudsen number square, Reynolds number. So, this is square divided by Eckert number, which is the ratio between the kinetic energy to enthalpy of the flow, into del T star over del x star at the wall. We can also write this is one form of the equation. We can also write as Knudsen number into 2 minus sigma v over sigma v into del u star over del y star at the wall, okay, plus 3 by 4 into delta T over T0, this is the temperature difference between the fluid and wall, into 1 over Re into delta T star divided by del x star at the wall. So, this is the second expression. Similarly, we can write for the temperature, no temperature jump boundary condition, or the temperature jump boundary condition in this case. So, T gas minus T wall, so which will be equal to 2 minus sigma T over sigma T into 2 k plus 1 into Knudsen number over Prandtl number into delta T star over delta y star at the wall. So, here K is the specific heat ratio, and EC is Eckert number, which is the ratio of the kinetic energy to enthalpy Cp delta T, and delta T is T gas minus T0. So, what we see here, if you look at the term 1 and term 2, if you look at term 1, what we see that if you are increasing Knudsen number, okay, then the thermal creep, this term which represents thermal creep, become more significant. So, thermal creep more significant if Knudsen number increases, okay. And we also observe from 2 is that the thermal creep increases as Reynolds number reduces. From here you can see that thermal creep is going to increase as the Reynolds number increase, or the Reynolds number reduces, or the delta T, the temperature gradient is increasing, okay. So, those are two important conclusions that we make from the non dimensionalization. So, with that let us stop here, and next we will be talking about slip flows for liquids.